Welcome back. So far we have seen the 5 meta-heuristic techniques, right? Artificial bee colony optimization, genetic algorithm, differential evolution, particle swarm optimization and teaching learning based optimization, right? In all the 5 cases when we were discussing these meta-heuristic techniques, we took only the objective function. There were no constraints apart from the bound constraints, and bound constraints we handled by corner bounding the solution. Whenever a solution violated the bounds, we brought it back to the bound. Right. So, first we will look into 3 examples, right. Subsequently, we will discuss how to convert those constrained optimization problem into unconstrained optimization problem and continue using those 5 algorithms which we have discussed. Right. The first example is a farm example, right. So, wherein 800 kg of special feed is required daily, right. So, the special feed can be prepared by a mixture of corn and soya bean meal. So, we have corn and we have soya bean meal. Right. Using these two, we need to combine these two to come up with at least 800 kg. Remember, this word at least is important, right. So, at least 800 kg, we can come up with more than 800 kg, that is fine, but at least 800 is required, right. Every kg of corn that we take, we will have 0.09 kg of protein and 0.02 kgs of fiber. Similarly, for every kg of soya bean meal we take, we will have 0.6 kgs of protein and 0.06 kgs of fiber. The cost of corn is $0.3 per kg and the cost of soya bean meal is $0.9 per kg, right. So, we need to come up with at least 800 kg. So, for example, now we can say since corn is cheaper, we will say all the 800 kg is nothing but corn, right, but there are constraints, right. The dietary requirements of the special feed. So, special feed is what we are preparing by mixing corn and soya bean, should have at least 30% protein and at most 5% fiber. So, if the protein content is more than 30, it is fine, but the fiber content should not be more than 5%, right. So, this is at most and over here it is at least. Right. So, first let us see how to model this problem. So, here the decision variables are, we do not know how many kgs of corn and how many kgs of soya bean are to be mixed, right. So, that is what is our decision variable, x1 and x2 are our decision variable, right. So, our objective function is to minimize the cost. So, the cost of 1 kg of corn is 0.3. So, the total cost of corn would be 0.3 into x1. So, x1 is what is the decision variable, which is what we want from the optimization procedure, and the cost of soya bean is 0.9. Right. So, the total cost of soya bean is 0.9 into x2. So, this is the cost of corn, this is the cost of soya bean. So, the total cost is 0.3 x1 plus 0.9 x2, right. So, that is the total cost and we want to minimize this, right. So, if we directly solve this problem, the answer is x1 is minus infinity, x2 is minus infinity, right. Since minus infinity does not make sense for this mass kg of corn, so the minimum quantity is 0. Right. So, the lower bound for x1 and x2 is 0. So, x1 and x2 have to be greater than 0. Right. So, if we just solve this problem, then we will get 0 is the cost, right, but we have constraints on this, right. The first constraint is that the total amount of material that we have, like whatever kgs of corn we take and whatever kgs of soya bean we take, the sum total of that has to be at least 800. Remember, this is at least. So, that is why it is greater than or equal to this is kg 800, right. The second constraint which we had was that at least 30% of whatever mixture we have should contain protein. So, the mixture that we have is x1 plus x2. So, the 30% of that, so 0.3 of x1 plus x2, this should be the minimum amount of protein which is to be there, right. So, we put this greater than equal to constraint over here, right. So, in the mixture that we take, so this is what is required, right, 0.3 of x1 plus x2. What we actually would have is this one 0.09 x1, because corn contains only 0.09 protein, right. So, 0.09 into x1. Similarly, soya bean contains only 0.6, right. So, 0.6 into x2. So, 0.091 x1 plus 0.6 x2 will be the amount of protein in x1 kg of corn and x2 kg of soya bean. We want it to be greater than or equal to 30% of the mixture itself. So, the mixture, the total amount of mixture is x1 plus x2. So, the 30% of that is on this right hand side, right. So, now if we simplify this equation, right. So, 0.09 x1 minus 0.3 x1. So this 0.3 x1 can be taken to this left hand side, right. So 0.09 x1 minus 0.3 x1, that will be minus 0.2 x1. Similarly, this 0.6 x2 minus 0.3 x2 will give 0.3 x2. So this is our constraint. This is second constraint, this is our first constraint, this is the objective function. Right. So we have one more constraint, right, which says that the total amount of fiber should be at the maximum 5%, right. So same thing, the amount of fiber content would be 0.02 x1, because corn has 0.02 and x1 is the amount of corn. So 0.02 x1 plus 0.06 x2, per kg of soya bean we have 0.06 kg of soya bean, and now we have taken x2 kg of soya bean. So the total amount of fiber would be 0.06 x2. So this has to be less than, because here it is at most, right. So that is why it is less than equal to 5% of the mixture. So 5% is 0.05 of the mixture. So just like we had x1 plus x2, here also we have x1 plus x2. Similarly, this can be simplified. So the x1 term can be taken to the left hand side, the x2 term can be taken to the left hand side, and we will have this equation, right. So as you can see, even for a simple problem we have constraints, right. So this is called the modeling phase. So given a problem description, so in this slide what we had was just the problem description. First this has to be modeled, right. So once we model, we have the problem description in a mathematical form, right. So this is the objective function and three constraints. So here if you see the type of problem, so we have x1 and x2 as the decision variable, right, and both of them are continuous. We do not have integer variables here, right. Let us say x1 is equal to 2.3 kg could be permissible. Let us see the objective function. This is a linear objective function in x1 and x2. So this constraint is also linear, x1 plus x2 greater than or equal to 800. This constraint is also linear, right, to the power 1, and this constraint is also linear. So in this problem we have two decision variables, right, one objective function, right, and three constraints. Both of these are linear. So the objective function and the constraints are linear, right, and the decision variables are continuous. So if you recollect our first introduction lecture, right, so this falls under the problem category of linear programming, wherein the constraints and the objective function are linear and the decision variable are continuous. So we will look at this second example, right. So in this example we have a paint company. This example is also taken from this book, Operation Research and Introduction by Taha. There is a paint company, Ready Mix company. It produces two types of paint, interior paint and exterior paint, right. So to produce this paint, it requires raw material 1, M1, and raw material M2. So M1 and M2. So for producing 1 unit of exterior paint, it requires 6 units of M1 and 1 unit of M2. For producing this interior paint, it requires 4 units of M1 and 2 units of M2. So the total amount of M1 that is available is 24, and the total amount of M2 that is available is 6. $5 of profit is made by selling 1 unit of exterior paint, and let us say $4 of profit are made by selling 1 unit of interior paint, right. So the question now is, how much of interior paint and exterior paint has to be produced, right. Determine optimum quantity of interior and exterior paints that has to be produced so as to maximize the total daily profit, right. So here there are two conditions, two additional conditions, that the maximum daily demand for the interior paint is only 2 units, right. So there is no point of producing interior paint more than 2 units because there is no demand, you cannot sell that in market, right. So that is one constraint. The other constraint is daily demand for interior paint, right, cannot exceed that of exterior paint by more than 1 unit, right. So we will see how to model that now. Now the question is, how much of paint 1 and paint 2 has to be produced, right. So that is the decision variable. So we are defining the two decision variable, x1 and x2. x1 indicates units of exterior paint produced daily, x2 indicates units of interior paints that is produced daily. So those are our decision variables, right. So here in this case, since these are units, these are integer variables. There is no meaning of 2.5 units, right. So the unit has to be integer, so it's like number of pens. So the number of pens can only be an integer value, right? So first we have decided the decision variables. So in this case the decision variables are integers. So if we produce x1 units of exterior paint and x2 units of interior paint, then the total profit is 5x1 plus 4x2. This has to be maximized, right? So maximized profit, we are indicating that by the variable z, right, is 5x1 plus 4x2. So right now this objective function is also linear. Then we have the raw material constraint, right? If you are to produce 1 unit of exterior paint, we require 6 units of M1, right? So if we are to produce x1 units, then we require 6 x1 units. Similarly, if we produce 1 unit of interior paint, we require 4 units of M1, right? So if we produce x2 units, we require 4 x2. So the total amount of raw material M1 that is required is 6x1 plus 4x2. So this has to be less than equal to 24, because that is the maximum amount that is available. It is not equal to 24 because it is not necessary that we use all the 24. We can use less than that also, right? So that's why we have this constraint less than equal to, right? Then similarly we can develop this constraint for raw material 2, right? So if we produce x1 unit, then the total amount of M2 that is required is 1 into x1 plus, because of this 2, because it requires 2 unit per unit of interior paint, so 2x2, this has to be less than equal to 6 because that is what is available, right? Right now we have one objective function which is linear, we have 2 decision variables which are integers, and we have 2 constraints which are also linear. So the next constraint is this one we need to model, right? Daily demand for interior paint cannot exceed that for exterior paint by more than 1 unit. So interior paint is x2, right? So it cannot exceed. So when we say it cannot exceed, it has to be less than equal to, right? It cannot exceed that for exterior paint. So exterior paint is x1, right, plus 1, because by more than 1 unit is problem specification, right? So this is the other constraint, x2 is less than equal to x1 plus 1, right? And then we have this constraint that x1 and x2 have to be greater than or equal to 0. We had this additional constraint that maximum daily demand for the interior paint is 2 units, right? So that is why we have x2 is less than equal to 2, because x2 indicates the units of interior paint, right? So now we have objective function which is linear, these 3 constraints which are linear, the lower bound of both the decision variables are 0, the upper bound of decision variable 1 is not explicitly given, the upper bound of variable x2 is given, x2 is less than equal to 2. This x1 may not have upper bound, right, but the other set of constraints will be bounding this x1, right. So in this case we have a integer linear programming, all the constraints and the objective function are linear, so linear programming, and both the variables are integer, so we have integer linear programming. So the next example that we will see is non-linear programming example. So in this case there is a river, right, and a farmer has fencing of 2400 meter. So this is the amount of fencing that the farmer has, right, and he wants to have a rectangular area, right. So the question is what should be the length of the rectangular area and what should be the breadth of the rectangular area. So what is this L, what is this B? The farmer doesn't know what has to be L, and the farmer does not know what should be the breadth, right, but the total amount of fencing material that he has is 2400 meter, right, and fencing is not required in this side, right. So the fencing is required only on the 3 sides, over here and over here. So the total amount of fencing is L plus 2B, right. So this should be less than equal to 2400, right. So here also remember he doesn't need to use all the 2400 meters of fencing, but at the maximum he has 2400 meters of fencing, right. So that is our constraint, right, and these two are logical constraints that L and B has to be greater than 0. The farmer wants to maximize the area. Area is given by L into B. So the objective function is now non-linear, right, in fact it's quadratic. L is for length, B is for breadth. So there are no explicit lower and upper bounds for L and B. So the problem is to find out the value of L comma B, L and B, such that L into B is maximum and it also satisfies this constraint. So over here if we see, this is a linear constraint, L plus 2B is less than equal to 2400. This is a linear constraint. So but this objective function is quadratic, right? So we will call it as nonlinear programming problem, or QP, constrained QP, because there is a constraint involved. Now we have seen three problems, right? The first problem was a linear programming problem, the second was an integer linear programming problem, the third one was a non-linear programming problem. In all these three problems, the problems were extremely simple, but even then there were multiple constraints involved. But the techniques we have seen so far are for unconstrained optimization problem. So now the question is, how do we accommodate the constraints, right, into this meta-heuristic techniques? So let us look at the types of constraints that we can generally have. So we can have inequality constraints as well as equality constraints, right? So inequality constraints are usually denoted by g of x is less than equal to 0. So if we have a constraint which has greater than or equal to 0, let's say x1 plus x2 has to be greater than or equal to 0, we have seen that this can be converted into this less than equal to form by multiplying with a -1 on both sides, right? In equality constraints, we have g of x is equal to 0, right. So solutions we classify into two types, feasible solution and infeasible solution. So feasible solution is one which satisfies all the constraints, and we are interested in feasible solutions. Infeasible solutions are those which violate at least one constraint. So if there is a solution which has a very good objective function value, but even if it is not satisfying one constraint, that solution is not useful for us, because we are interested in feasible solutions, and among feasible solution, the one that is the best is what we are looking for. These are the three conditions that we need to satisfy, that given any two solution, right, a feasible solution is preferred to any infeasible solutions, so irrespective of the objective function value. And if we have two feasible solutions, right, so both the solutions satisfy all the constraints, then the one having a better objective function value is preferred, right. And in case if we have both solutions which are infeasible, right, the one which has a smaller constraint violation is preferred, right. So here if we see, in these three rules we are actually giving more weightage to feasibility than the objective function, right. So objective function plays a role only if both the solutions are feasible, right. And if we have a feasible solution and infeasible solution, we do not worry about what is the objective function value, we select the feasible solution. And in event wherein we have two infeasible solutions, we will be selecting the one which has lower constraint violation. So we are taking two solutions, xi and xj. Xi is said to be constraint dominate xj if xi is feasible and xj is not. So that corresponds to this condition. We have a feasible solution and an infeasible solution. So the feasible solution is to be preferred. So xi is said to constraint dominate xj, right. And if it happens that both xi and xj are infeasible, right. So we are looking at the third case now. So if both of them are infeasible, then xi is said to constraint dominate xj if xi has a smaller constraint violation than xj, right. Similarly, this corresponds to the second case, wherein both xi and xj are feasible solutions. Xi is said to dominate xj if it has a better objective function value than xj, right. So it is the same three rules we are explaining again with taking two solutions, right. So now let us look at an example. Let us say we have these four solutions, S1, S2, S3, S4, right. This is the decision variable x. So let us say it is a single variable optimization problem given over here, that we want to minimize f, which is nothing but x by 2, and we want to satisfy this constraint, x square should be greater than or equal to 0.45 and x is between 0 and 1. So x has to be greater than 0 and it has to be less than 1, right. So these are the four values of the decision variable x corresponding to solution 1, solution 2, solution 3, solution 4. These are their corresponding objective function values, right. And since we know this is 0.7, we can check whether 0.7 square is greater than or equal to 0.45. In this case it satisfies this constraint, so the violation is 0. Even in this case you can check that 0.8 square would be greater than or equal to 0.45, right. So this also satisfies, whereas in these two cases x is equal to 0.4 and x is equal to 0.65, if we take x square it will not be greater than or equal to 0.45, right. So it will be violating that constraint by this much amount, by 0.29 and 0.0275, right. So now let us say this is our population, right, and if we are to select from this four solutions, let us say we are working with teaching learning based optimization, this is our population, right, and we are now supposed to select the teacher, and we are working with the minimization problem, right. So, we are not supposed to go by this point 2, right, because it has a better objective function value, but it also violates the constraint, right. So, in that case we need to first find out what are the feasible solutions. So, the feasible solution here is S1 and S4. Between S1 and S4 we would select S1 because it has a better objective function value, right. So, here if we see S1 constraint dominates S2. So, let us take S1 and S2, right. So, S1 is feasible, S2 is infeasible. So, obviously S1 constraint dominates S2. In the second case S3 and S2 we are comparing. So, in this case if we see both of them are infeasible solution, right. So, that is why it is listed over here. The violation over here in S3 is less compared to in S2, right. So, that is why we say S3 constraint dominates S2, right. And the last case is between S4 and S1, right. So, in this case if we see that S1 actually constraint dominates S4 because S1 has a better objective function value. So, this has to be S1 constraint dominates S4, right. So, because we need to go by the objective function value. So, these are the 3 rules that any constraint handling mechanism that we will study should ideally follow these 3 rules, that between 2 feasible solutions we will select the one which has better objective function value, between 2 infeasible solutions we will select the one which has lower violation of the constraints, between 2 feasible solutions we will select the one which has a better objective function value, and between a feasible and infeasible solution the choice is very clear that we will not worry about the objective function value, we will go with the feasible solution. Sometimes we can reduce the number of constraints that we have. So, for example, consider this problem. This is a 3 variable problem. We are supposed to find out the values of x1, x2, x3, right, such that this function 3x1 plus 2x2 plus x3 has the minimum possible values, and we need to satisfy these 3 constraints, right. So, we have 2 inequality constraints and 1 equality constraint. So, the value of x1 and x2 should be such that x1 minus x2 should be equal to 2, and x1 plus x2 plus 0.5 x3 should be less than or equal to 4, and 2x1 plus x2 plus x3 should be greater than or equal to 5. So, in this case we can directly take this problem, right, and say that we are having 3 decision variables, or what we can do is we can exploit this constraint, right, and reduce the number of decision variables. So, for example, this constraint we can rewrite it as x2 is equal to x1 minus 2, or we could have chosen as x1 is equal to 2 plus x2, right. Either we could have used this or we could have used this. Now, I can use this relation to completely eliminate x2 from all other equations, right. Instead of writing 3x1 plus 2x2 plus x3, we can say 3x1 plus 2 times x1 minus 2 plus x3, right. So, that should work out to 5x1 plus x3 minus 4. Similarly, we can get rid of x2 from this equation, we can get rid of x2 from this equation, right. So, this problem which had 3 decision variable, 3 constraints has been reduced to 2 decision variable with 2 constraints, right. So, we exploited this equality constraint. So, we can choose to solve this problem instead of this problem, right. So, here the number of decision variable is less, so our search space is also less, right. So, the algorithm is typically expected to perform better on this problem than on this problem, and once we solve this problem we will get the values of x1 and x3, right. Once we have the optimal value of x1 and x3 from any of the 5 algorithms which we have studied, right, then we can actually calculate x2 from this relation, right. So, x2 can be obtained at the end. So, in this case we have implicitly handled this constraint, right. We use this constraint to completely eliminate one variable, right. So, that way we have also taken care of that constraint, and while taking care of that constraint we have also managed to eliminate one decision variable. If there is an optimization problem with n decision variables, and if there are k linear equations, right. So, this is a linear equation. If there are k linear equation, then we can derive k relations, right, and use them in the optimization problem to convert this n variable optimization problem into a problem with n minus k decision variables, right. So, this is one way of handling the constraints. So, if it is an explicit equation we can do it, right. Let us say if we have an implicit equation which says, let us say x1 power x2 power x3 has to be equal to 5, right. In this case what we can do is we can completely eliminate one variable, right. We can have just 2 decision variable x1 and x2, right? And once we have these two variables x1 and x2, we can actually solve this equation, that x1 power x2 power x3 minus 5 is equal to 0, and get the appropriate value of x3, right? So either we can choose to eliminate variables like this, or if we are not interested in eliminating variables, we can still have those equations as such. So this figure you might remember, right? So the algorithm generates randomly one solution or a set of solutions, right? So previously whatever we had seen in that for unconstrained optimization problems, it was generating all the decision variables, right? So here we can say that it will generate only partial decision variables. So for example, in this case, it will generate only x1 comma x3. Right. So this partial set of decision variable is sent through the problem statement. Here we would have this equation that x2 is equal to x1 minus 2, right, and calculate x2, right. Once we know x2, x1, x3 is given by the algorithm, x2 is generated over here. So we can calculate the objective function, we can check for the constraint satisfaction, right, whether it is satisfying these two constraints or not, because now we know all the values x1, x2, x3 are known, right. So we can check for constraint satisfaction. Depending upon whether it is satisfying constraints or not, or how many of the constraint it is satisfying, or how much is the violation, we will see procedure to come up with this fitness function value, which is what will be returned back to the algorithm, right. So this way we can make use of equality constraints to reduce the number of decision variables, instead of explicitly handling them as constraints. So in unconstrained optimization problem, right, whatever the objective function value was, that was the same as fitness function, right. So for all the problems, that's what we did, except for ABC, right, because in ABC we had that fitness function was inversely related to the objective function, right. Otherwise in all the 4 algorithms, the fitness function was nothing but the objective function value. That is true only in the case of unconstrained optimization problem. When we have constrained optimization problem, what we will do is we will add a penalty, right. So what we are doing is, for those solutions which does not satisfy the constraint, we will calculate something called as penalty, right, and we will add it to the objective function. This is true for minimization problem, right. For maximization problem, it has to be objective function minus lambda times penalty, right. So what we are basically doing is, we are deteriorating the objective function value using the penalty, right. We are adding the penalty because the solution is not satisfying one or more constraints, right. So for example, let us look at these two solutions, solution 1 and solution 2. Let us say for some arbitrary objective function, the objective function value of solution 1 is 5, the objective function value of solution 2 is 7, and let us say this is a feasible solution, this satisfies whatever the constraint, and this does not satisfy the constraint, right, and the violation is 0 because the solution is feasible. So it is not violating any constraint, so the violation is 0. Let us say for a particular constraint the violation is 2, right. So in this case, if we take lambda is equal to 20, right, and we apply this equation, objective function plus lambda times penalty, right. So here, since the violation is 0, right, so this is violation or penalty, right. So since this is 0, if we apply this equation, this 5 will continue to remain as 5, right, whereas this 7, right, will become 47, because now the fitness function is 7 plus 20 times 2. So this is 40 plus 7, 47. So that is this particular value. So once we calculate the fitness function, we do not need to worry about whether the solution is feasible or not, right, because the fitness function actually captures whether the solution is feasible or not. So let us consider this case. We have one more solution, S3, and let us say it is also not a feasible solution, right, and the violation of some constraint is to the magnitude of 0.1, right. So now if we go just by the objective function, this solution would be picked up. So for example, remember we were identifying the teacher by looking at the least value, right. So in that case, this will be picked up. So that is why we do not want to work with objective function when we have constrained optimization problems. We want to work with fitness function, right. If we have taken lambda value as 20, in this case what will happen is, it will be 2 plus lambda is 20 into violation is 0.1, right. So this will become 4. Actually between these 3 solutions, which one do we want to select according to the 3 rules which we have seen? Both of these are infeasible, right. So this is the one which has to be selected. But now within TLBO, if we look at what is the minimum value among these three solutions, right, this one would be picked up, S3 would be picked up. So S3 is getting picked up, but what we want is S1 to be picked up, right. So this happens because the lambda value is not appropriately chosen over here. So if we choose a lambda value of, let's say, 200 instead of 20, which we discussed previously, if we take 200, then this solution will continue to be phi because it is a feasible solution. No matter what is the value of lambda, the penalty or the violation is 0, right. So the objective function is the same as fitness function value, whereas this 7 will now become 7 plus 200 into 2, right. So this becomes 407, and this 2 becomes 2 plus lambda is 200 into 0.1, right. So this will become 22, right. So now if we pick up the best solution from this fitness function value, right, so the best value is phi, right. So S1 would get picked up, which is what we wanted in the first place, right. So this lambda helps us to handle the constraints, right, but the value of lambda has to be appropriately chosen. If a poor value of lambda is chosen, then that rule that between an infeasible solution and a feasible solution we want to pick up the feasible solution would get violated, right. So this lambda has to be appropriately selected. So far what we were doing is we just told you that take the violation as 0, because here you can understand it is 0 because the solution is feasible. In these two cases we just said that take the violation is 2 and 0.1. So now let us take an example and see how to actually come up with this violation value. So let us assume that this is the problem that we are given, minimize f of x, right, and there are j constraints, right. So this g of j of x is greater than or equal to bj. So j constraints are given, and xi we have I variables, right, and all of them have a lower and upper bound, right. So first thing is to normalize this constraint, right. So normalize this constraint in the sense like divide the coefficients in this constraint by bj. So we will have bj by bj, so this will become 1. We want all the constraints to be of this form. So the first step is to normalize the constraint. Once we have normalized the constraint, we need to find out the extent of violation. So in this case, remember, when we are working with meta heuristic algorithms, we would have the decision variables, the value of the decision variables, right. That is what the algorithm gives. No matter which algorithm you are working with, it will give you the value of the decision variables. So once we know the value of the decision variable, we can actually check whether the constraint is satisfied or not. So this is something that we can check. So for example, let us say the constraint is x2 square plus x3 should be greater than or equal to 0. So now we will have the value of x2 and x3. So we can actually check for this condition, right. So let us say if this is 2, this is 8, we can actually check for this condition. So we will calculate this, and if it happens to be greater than or equal to 0, then this omega j is taken to be 0, else if it is less than 0. So for example, let us say this happens to be minus 5 for some value of x2 and x3, then this omega j is equal to absolute of this violation. So what we are calculating is the violation, so the absolute of that, right, because this is going to be a negative value, right. It comes into this part only if g of x is less than 0, right. So we take the absolute value of that. That is how omega j is calculated, right. So if we have 10 constraints, we will have 10 such omega values. The next thing is to estimate the total penalty. So the total penalty is nothing but taking the summation of all the individual penalties, right. So let us say first constraint we are violating by 5, second constraint we are violating by 3, third constraint we are violating by, let us say, 15, right. So this capital omega is nothing but a scalar value which will be 23, which is nothing but the summation of this, right. So once we have calculated this omega, the fitness function f is the objective function, right, plus the violation, right, multiplied by Rm. So Rm can be a constant value. So this is what we saw as lambda in the previous slide, right. So usually this penalty factor is one order of magnitude higher than the objective function value, so that when we are comparing a feasible solution and an infeasible solution, the feasible solution actually wins over the infeasible solution, right. To simplify, you can just consider this as x, right. You do not need to look at x of I. So Rm has to be a magnitude higher than the objective function. Since we are working with minimization problems, it has to be a magnitude higher than the objective function. So now let us consider an example, right. So let us say this is our objective function. We have two decision variables, right, x1 and x2, right, and the two constraints which we have is 9x1 plus x2 should be greater than or equal to 6 and 9x1 minus x2 should be greater than or equal to 1. Right. So, we have an objective function involving two decision variables, we have two constraints, right, these are not equality constraint. If it had been an equality constraint and since this is linear, we could have used it to eliminate a variable, right. So, right now we cannot do that, right, and the two decision variables x1 and x2 have their own bounds. So, x1 has to be between 0.1 and 1 and x2 has to be between 0 and 5. Right. So, first step is to normalize the constraint, right. So, this is what we want to do. So, over here this is normalized constraint, right. So, how do we normalize this? 9x1 plus x2 divided by 6. So, we will have a 1 over here, right. If we take 6, then we bring the 1 to the left hand side, so that we get the constraint in this form. So, 9x1 plus x2 by 6 minus 1 should be greater than or equal to 0, and similarly we can transform the other constraint, right. So, these two constraints are nothing but the normalized form of these two constraints. Right. So, now let us consider these 6 solutions. Since it is a 2 variable problem, let us consider the values of x1 and x2 as given over here, right. So, this may be our initial population, right. So, for initial population the first thing that we need to do is calculate the objective function, right. So, this is the objective function which is nothing but plugging in these values x1 and x2 in this equation, f of x is equal to 1 plus x2 by x1. So, we will be able to calculate these 6 values, right. So, on the basis of this, if we were to pick up the best solution, right, we might pick up solution 6.10, right. So, but if you plug in these values of x1 and x2 and plug into these two normalized constraint, you will see that these two values do not satisfy G1, right. So, this is G1 bar, G2 bar, they do not satisfy this constraint. So, the first solution does not satisfy G1, but it satisfies G2. Right. Similarly, the second solution satisfies G1, but does not satisfy G2. The third solution does not satisfy G1, but satisfies G2, whereas the rest of the solutions, right, satisfy both the constraints, right. So, the first 3 solutions are infeasible, the last 3 solutions are feasible. So, if we were to select what is the best solution among this, right, we would actually go with 7.74, right. Though it has a poor objective function value than S1, it is a feasible solution, whereas S1 is an infeasible solution, right. So, this is what we want to happen, right, but what we can actually supply to the algorithm is just a fitness function value corresponding to each of this solution, and then the algorithm is going to select the best solution, and we want the algorithm to actually select S6 and not S1, right. So, the only control that we have is over the fitness function which we are passing to the algorithm, right. So, what we can do is calculate this omega 1 and omega 2, right. So, for these solutions wherever it is infeasible, so this is 0, this is also 0, this is 0, 0, 0, 0, 0, 0, 0. So, wherever it is feasible, the omega value would be 0 because it is satisfying the constraint, right. So, the constraint is greater than or equal to 0. So, that is why we take omega as 0, right. But for the other 3 cases, we would be able to calculate the amount by which it is violating, right. So, once we have both of these omega 1 and omega 2, right, that is calculated using this equation, right. Subsequently, we can just sum both the penalties 0.39, 0.31, 0, 0, 0 by adding its respective omega 1 and omega 2, right. So, this is the total penalty value. So, we have now estimated this, right, and for this case we are taking RMS 20. So, this RM has to be selected for a particular problem, right. So, it has to be selected in a way such that all the 3 rules which we have discussed, right, should be satisfied. So, now we have the objective function here and we have the total penalty here, and the equation for calculating fitness is here, right. So, it is 6.10 plus 20 into 0.39. So, this will work out to be 13.90, right. So, similarly, the fitness function for all of these solutions can be calculated, right. So, since these 3 solutions are feasible, it satisfies both the constraints. So, both the omegas would be 0 for the feasible solutions. So, the summation of them is also going to be 0, right. So, the objective function is nothing but the fitness function for a feasible solution, right. So, that is why for these 3 solutions you can directly tell the fitness function without necessarily calculating W1, W2 or omega. So, now among these 6 solutions, right. So, if our algorithm is to pick it will pick 7.74, right, because that is the least value in this. So which is what we actually wanted the algorithm to do. We wanted the algorithm to pick S6 because it is a feasible solution and it has the best objective function value among the feasible solutions, right. So this is what we will return in constraint optimization problem. So in unconstrained optimization problem, we don't need to worry about constraint because there are no constraint. There may only be bound constraints which can be taken care by the corner bounding strategy which we discussed, right. For unconstrained optimization problem, there are no constraints, right. So objective function is the same as fitness function, whereas for constrained optimization problem, right, we calculate the amount of violation and we add it to the objective function. For a minimization problem, we add it to the objective function with a factor lambda or Rm. The value of lambda or Rm should be such that a feasible solution should be preferred over an infeasible solution. If you remember, we had one example in the previous slide wherein we had chosen a lambda value of 20 and that did not work out for the solution S3, right. So we should ensure that a feasible solution always wins over an infeasible solution, right. So in all these cases we knew the solutions, right. So it was easy to choose a lambda value which actually worked out. For an arbitrary problem, the selection of lambda should be carefully done. So the same problem, right, so we solved using TLBO, right. So it's the same problem over here. This is the normalization of those constraints and then we applied TLBO. Remember, we don't need to do any change in the algorithm, right. So previously what we were doing in unconstrained problem is we were receiving x and we were sending the objective function value O, right. Now communication is the same thing, right. We will receive x and what we are sending back is the fitness function value. So this is the algorithm, this is the objective function or the problem, this is all algorithm, the problem. So whatever the constraints are there are taken care over here, right. So still we are just passing a scalar value for a particular solution. So if we get one solution, we would still be passing just a 1 cross 1, right. So if this is 1 cross D, we will just pass a 1 cross 1. So for this problem, Rm is equal to 20, right. So here is the iteration counter. So this is a video. So once we play, you will see this iteration counter changing. These are our initial 5 solutions, right. So this is the infeasible region, right. So those both the constraints we have plotted, right. So 9x1 minus x2 equal to 1 is this line. So we have plotted both those constraints, right, and this is the infeasible area, right. So initially all the 5 solutions which we randomly generated are in the infeasible zone, whereas this is our feasible zone. So what we are expecting is, as the algorithm proceeds, we expect the solutions to move, right, to a feasible region, and once they have moved to a feasible region, they would start finding better solutions, right. So as you can see, all the 5 solutions are moving, right. So they have moved now into the feasible region, right. So along the feasible region, they are still searching for a better fitness function value. So we run it for 50 iterations. You can see the iteration counter over here, right. So at the end of 50 iterations, all of the solutions seem to have converged to a particular point, right. In the previous case, what we did is we added a penalty which was in proportion to the violation, right. But if some condition is not satisfied, we can add a constant value, right. No matter how much the violation is, right, we can add a constant value. So we have j conditions. For each condition which is not satisfied, we can assign a penalty which can be added to the objective function to determine the fitness function. So for example, it is not necessary in meta-heuristic techniques that all the constraints have to be this form. Let us say x1 plus x2 is greater than or equal to 0. So this constraint can be handled by meta-heuristic techniques, right, but meta-heuristic techniques can also handle this type of constraints. So I want, let us say we have 2 variables x1 and x2, and this is the condition that we have, right. So basically this is a constraint that the value of x1 and x2 should not be the same. So if the value of x1 and x2 is same, right, we want to assign a penalty, right. So in that case, we can merely write this condition that if x1 is equal to x2, we will say lambda is equal to, let us say 10 power 5 and end, right. If we have m such conditions, right, x1 not equal to x2, x1 not equal to x3, x1 not equal to x4, we will have that many values of lambda, right. And here if we see, we are directly assigning a value. So it does not matter what is the value of x1 and x2. If they are equal, we add a constant value. So that we will be calling it as hard penalty, right. So irrespective of the amount of violation, we add a penalty. So this lambda value itself is selected in such a way that we don't need to include a lambda over here, right. So this is sufficiently big such that whatever the role this lambda was playing here, right, in the previous slide we had seen f is equal to f plus lambda times the penalty, the total penalty, right. If it is calculated in such a way that it is able to capture the feature that a feasible solution will always win over an infeasible solution irrespective of the objective function value, it is fine. So this is the one that we have discussed in the previous slide, right, using a penalty function. In the previous slide we had considered only the case of inequality constraint. So similarly we can also consider for equality constraints. Let us say we have a constraint x1 plus x2 square plus x3 cube is equal to, let us say, 5. So we will convert this constraint into x1 plus x2 square plus x3 cube by 5 minus 1 equal to 0, right. So once we have the values of x1, x2, x3 from the algorithm, we will calculate this left hand side, right. If it is equal to 0, then we do not assign penalty. If it is not equal to 0, whatever that value is, that is considered to be the amount of violation. Here if you see, we have this operator over here. So this basically does what we have discussed previously, right. So this operator is nothing but it will assign a value of 0 if the constraint is satisfied, if the constraint is not satisfied. So if it is a negative value, right, then it will take the absolute of this. So for example, consider this case that g of x is equal to minus 2. Since it is less than 0, it actually violates the constraint. So this bracket operator will take just the absolute of this. So absolute of minus 2 is equal to 2. But if g of x was actually 2, right, so then this bracket operator will return 0. So this bracket operator is doing exactly the same as we have done in the previous slide for calculating w, right. So w was absolute of gj of x if it is violating the constraint, else it was 0, right. So compactly, instead of writing this big expression, right, we can directly use the bracket operator over here and sum those penalty. So there are capital J number of inequality constraints and capital K equality constraints. So the violation in each is to be added to the objective function with an appropriate lambda value, right. This is either lambda or Rm, and that is how we determine the fitness function value, right. So here it has to be for j is equal to 1 to j and for k is equal to 1 to k. So the number of inequality constraints and equality constraints need not be same, right. So for equality constraint we are using this index k, for inequality constraints we are using this index j. There are couple of other procedures, right. So one is dynamic penalty function, wherein this we have a power beta over here and over here we have a power beta. So beta is a user defined parameter. So this c and alpha again are user defined parameters. So in addition to the algorithmic parameters, for a problem we need to specify lower bound, upper bound, the objective function value. So if we choose to use this method to calculate the fitness function, we also need to specify what is alpha, beta and c, and here t is the iteration counter, right. So over here if we see, this term t appears over here. So in this case what is happening is this penalty value is changing, this is no longer a constant, right, it is changing as the iteration progresses. So the usual value of beta that is suggested is 2, right. Additional details about this dynamic penalty function can be looked into this book, which again refers to a article. So this is dynamic penalty function, right. Other method that we have is based on feasible over infeasible solution. So we want to prioritize feasible solution over infeasible solution, right. So this term f of x is the objective function, right, this term we have discussed. So this r t comma x is difference between the best static penalized function value among all infeasible solutions. So let us say we have 100 solutions, right. At the bottom we have placed those infeasible solutions, let us say 25 infeasible solutions are there. So among the infeasible solution, which is having the best static penalized function value, right, best static penalized function value is this term, right. So that term and the worst feasible value, right. So we will have a particular scalar value corresponding to this, and then the worst feasible solution. So we have, let us say, 75 other feasible solution. Among this there will be a solution which has the worst objective function value. It is feasible, but it is the worst objective function value. So since all these 75 solutions are feasible solution, we can directly compare the objective function value. The one which has the worst objective function value, that value and the best static penalized function value among all infeasible solution. So, the difference between that can be added for all these 25 solutions. So, if you actually work this out, you will see that the best infeasible solution and the worst feasible solution will have the same fitness function value, and similarly this RT of x is getting added to all the other 24 solutions also, right. So, this is another way to determine fitness function, which is how we handle the constraints. Another way to handle constraint is using this F max, right. So, if a solution is feasible, then the fitness function is nothing but the objective function value, which is clear, right. But if a solution is infeasible, so far whatever strategies we have seen, even if the solution is infeasible, we were determining the objective function value, right, which is kind of not necessarily correct, right. So, for mathematical problems you plug in some values, so you will get some value for the fitness function, but let us assume that we are to perform an experiment and the experiment can be performed only for feasible values, right. So, then for infeasible values, calculation of this objective function itself is not possible. In those cases particularly this strategy helps, right. So, here it is the objective function is the same as the fitness function if the solution is feasible. If the solution is not feasible, right, so in this case, so otherwise is infeasible solution, we calculate the penalty. Since the solution is known, we can plug into the equations and we can check whether it is satisfying the constraints, right. So, since we are saying that it is an infeasible solution, we will be able to calculate these values. So, so far we had f all these places, right. What we are doing is f max, right. So, f max is the objective function value of worst feasible solution. So, in this case, let us say we have this 100 solutions, let us say 75 are feasible and the remaining 25 are infeasible. Then for these 25 solutions, we do not calculate the objective function value, right. What we will do is the worst objective function value, whatever is over here, that will be taken and the penalty for all these 25 solutions would be added. So, in this way, if you see, it will satisfy our requirement that none of these 25 solutions will defeat any of these 75 solutions, because what we are adding over here is the worst possible solution. Let us say we have 1, 2, 3 like this, let us say till 75. So, here what we are doing is 75 plus the penalty 1, right, for the 76 solution, 75 plus penalty of 2, right. So, we are doing this. If any of the infeasible solution and feasible solution are going to have a competition, the infeasible solution will always lose out, right, because this is the worst and we are adding something to it, right. So, this is a very nice strategy wherein we do not even need to spend computational effort to find out the fitness function of a infeasible solution. So, this strategy can also be adopted, right. Again, remember, all of this is true only for minimization problems, right. So, for maximization problems we will have to appropriately change it. So, for minimization problem we say the fitness function is f is equal to the objective function plus whatever that penalty is, right. Whereas for maximization problem it has to be fitness is equal to f minus penalty, right, or you do not need to worry about this, convert whatever maximization problem you have to a minimization problem and that will take care of this penalty. So, the penalty can be either hard penalty or it can be a constant penalty depending upon the amount of violation, or it can be an adaptive penalty wherein as iteration progresses we change the penalty factor, right. And the final one that we looked at is that we do not even calculate the objective function value of the solution which is infeasible, right. We just work with the worst feasible solution and we add that to the violation of the infeasible solutions. This is how we can handle constraints in meta-heuristic techniques. Now that we know how to handle the constraints, let us solve the problem using teaching learning based optimization, right. So, we have the TLBO code here. This is the same code that we have explained to you previously, right. So, we are not going to change anything over here. Remember, the way still we are handling problem is this is our algorithm, right, and this is our problem, whether it is constrained optimization or unconstrained optimization, right. So, right now the communication is the algorithm is going to give the decision variables and the problem is going to give the fitness function value, right. So, if it was unconstrained optimization problem, it would have returned just the objective function value. In the case of constrained optimization problems, it will return the fitness function value, which will also consider the violation of the constraints, right. So, we are not going to change anything in the algorithm is going to remain as such, right. So, whatever constraints we have, right, is part of the problem and will be handled over here. So that is why we will not be making any changes to the algorithm as such, right. So the algorithm remains the same. This is the script file, right. So which is going to call the algorithm to solve the problem, right. So we need to provide the lower bound, upper bound. So what we will do is we will take the same problem to solve. It is a 2 variable problem. So the lower bounds are 0.1 and 0 and the upper bounds are 1 and 5. So that is what we are defining over here, 0.1, 0, 1, 5. So lower and upper bound is defined, right, and this is the function file in which we are going to define the problem. So we say fitness function is equal to at prob. So fitness function is now a function handle, right. So whenever we are accessing fitness function, we would actually be accessing this file prob. Right. So to TLBO we pass the fitness function, which is the optimization problem that we want to solve, the lower bounds, the upper bounds. Here we have taken a population size of 5 and the number of iterations to be 10, right. So again no changes in this script file, right. So here we need to define the problem. So as we know from the algorithm, we are going to get the decision variable x. So in this case, since there are 2 decision variables, we will have x of 1 and x of 2, right. So this penalty factor we are fixing it to be Rm is equal to 20, right. So W is a row vector of 2 columns, right, because we have 2 constraints. Remember, this 2 is not related to the number of decision variable, it is because we have 2 constraints, right. So for each constraint we are going to check what is the amount of violation, right, and we are going to assign it to W. Right. So first constraint that we have here is 9x1 plus x2 by 6 minus 1, right. So that is what we have here, 9x1 plus x2 by 6 minus 1. So we are calculating the left hand side. So if this left hand side happens to be greater than 0, then we do not need to penalize, but if it is less than 0, we need to calculate the omega values, right. So what we are doing is exactly what we had seen previously, right. So this is what we are calculating as of now using that W. So we transform the constraint into this form, the normalized form, and then we are calculating this absolute. So if it is otherwise, so if the constraint is satisfied, if it is greater than or equal to 0, we do not need to assign any value of W because already it has been initialized to 0, but if it is less than 0, we need to calculate absolute of the left hand side of the constraint, provided the right hand side is 0, right. So that is what we are calculating, G of 1. So this is the left hand side. If it is less than 0, we calculate W1. If it is greater than or equal to 0, we do not do anything because W of 1 is anyway 0. Right. So similarly the second constraint we are handling. So the second constraint is 9x1 minus x2 minus 1 should be greater than or equal to 0, right. So 9x1 minus x2 minus 1. So we are calculating the left hand side. Again, if it is greater than or equal to 0, we do not need to do anything, else if this value happens to be less than 0, right, we need to take absolute of this G of 2 as the amount of violation, right. So we have calculated both the W's, then we calculate this omega variable, which is nothing but sum of the W vector, right. So the violation of first constraint plus the violation of second constraint, that is what we will get by sum of W. This f is our objective function, right. So objective function in this case is 1 plus x2 by x1, right. So here we write 1 plus x of 2 divided by x of 1. Again you need to take care of this brackets properly, right. So x of 1 is in the denominator and the numerator is 1 plus x of 2. So that is our objective function f, lowercase f. The uppercase f is the fitness function. Since it is a minimization problem, objective function plus Rm. So Rm we have as of now taken to be 20. Again Rm has to be tuned accordingly and would vary from problem to problem. Rm into omega, this violation. So that is what we had seen over here. So this is what we are calculating, f of x is equal to f of x plus Rm into omega, right. So that will return the fitness function value. So as and when we get a solution x, it will see if there is any violation in the constraint. If there is any violation in the constraint, it will calculate the appropriate violation, like what is the magnitude of violation, and then with the help of penalty factor we add it to the objective function, right. We add it to the objective function because our algorithm is a minimization algorithm and the problem is also a minimization problem, right. So we add over here, right. So this will return the fitness function value. Let us just execute this and see the determination of fitness function for one solution, right. So all these steps I will just skip because I presume you know them, right. So the first solution is being sent to this prob, right. So, this prob is nothing but this prob function, right. So, it will come to this file. So, we define Rm as 20, right, W as 0, right. So, G of 1 we are calculating. So, G of 1 turns out to be 0.0139. So, which is greater than 0, right. So, there is no violation of this constraint. So, it will not go into this loop, right. So, it skipped this, right. In this case, if we see G of 2 is greater than 0. So, it will again not get inside this if condition, right. So, W will still be 0 because W1 was not calculated, W2 was also not calculated because the solution satisfied both the constraint, right. So, in this case omega is equal to 0, this is the objective function f 5.3853. So, the fitness function will also be 5.3853 because this omega is 0, right. So, right now what we have got is the randomly generated solution is also a feasible solution over here. So, the fitness function of the first solution has been calculated. Let us look at the second solution. So, for this solution if we see it is 0.1233 and 1.0232, right. So, let us see if it is getting into this loop, right. So, if we calculate this value, G turns out to be minus 0.6445, right. So, that is actually violating the constraint. So, this right hand side over here is supposed to be greater than or equal to 0, but since it is less than 0, we need to calculate what is the violation. So, violation is nothing but G of 1 would be negative. So, absolute of that, right. So, that is W. So, in this case it violates the second constraint also, right. So, the second constraint value is minus 0.9132, whereas it is supposed to be greater than or equal to 0, right. So, again W is calculated, right. Sum of both the penalty values will give us this omega, which is 1.5577, right. So, this is the objective function which is 16, right. So, now we need to calculate the fitness. So, the fitness function is going to be f, which is 16.4046 plus this 20 Rm into this omega, right. So, here if we see the fitness of the second solution is 47.5586. The first one was a feasible solution, right. The second solution, which was randomly generated, is actually a infeasible solution, right. Though it is a constraint optimization problem, we have still managed to get back a scalar value from the problem, which is the fitness function value, right. So, similarly this will be calculated for all the 5 members, right. So, let me just skip that, right. So, here if we see it has calculated for all the 5 members, right, and the rest of the procedure is same. This is the iteration loop, the first solution that is being created, right. So, this is the new solution which has been created. Fitness function of the new solution is also to be evaluated, right. Again it will go into this function file. So, every time this is being accessed with this prob, it will go into this problem file, and then this is the greedy selection, right. So, if the new solution is better, it would be taken into the population, right. This is the learner phase. Again a new solution would be generated. So, the new solution generated here is 0.4735 and 0.5171, right. So, the bounding procedure, and again the new fitness function value is obtained by passing the solution to this prob, right. And then again we have a greedy selection mechanism, right, and this iteration loop continues, right. So, if we just remove this debug and then if we just do this continue, it will complete all the iterations. So, now if we see the best solution that it has determined is x1 is equal to 0.7126 and x2 is equal to 0, right. The fitness function corresponding to this solution is 1.4033, right, and if we look at this best fit iter, right. So, we had 10 iterations, but there would be 11 values over here because we also store the best fitness function value in the initial population. So, that was 5.3320, right. So, as we can see, as the iteration progresses, TLBO for a constrained optimization problem. Previously we had seen something similar, right, but that was an unconstrained optimization problem. Here for a constrained optimization problem, same thing happens. As far as the algorithm is concerned, whether it is a constrained problem or unconstrained problem does not really matter, right. The way we are using it, it does not matter whether the problem is an constrained optimization problem or unconstrained optimization problem, because in both cases the algorithm sends the solution and the optimization problem is supposed to send back the fitness function. If there are no constraints, the objective function is the same as fitness function, but if there are constraints, then the violation has to be considered along with the objective function value to determine the fitness function value. So, when we get the solution 0.7126 and 0, we do not really know whether it is feasible or not, right. So, what we need to do is go back and plug this solution into this file and actually see what is g of 1 or g of 2, or we can slightly modify this TLBO code so that we also get to know whether the reported solution is a feasible solution or not, right. So, in this case what we can do is we can directly use this file, right. So, let me just put a debug over here, let me just execute this function file from here, right. I am just checking whether the solution which we have obtained 0.7126 and 0 is feasible or not, right. So, if we plug this solution, right, so I am calling this function now prop and the input I am giving is bestsolve, right. So, bestsolve will become x inside this function file, right, and x of 1 is going to be 0.7126 and x of 2 is going to be 0, and since I am putting a debug button over here, I am going to have control over this function, right. So, if we do just F11, right, it did not go to the line 9, it did not go to the line 15. So, in this case both the constraints are satisfied. So, omega would be 0, f would be the same as what we have observed here 1.4033 because this omega is 0, right. So, 1.4033 and this f will also be 1.4033. So, this solution what we have got is actually a feasible solution, right. So, in the later part what we did is we just plugged that solution and just checked whether the solution is a feasible solution or not. So, if you have reasonable coding skills, what you can do is you can also vary this value of Rm, right. Either you can manually vary every time and then execute, or you can just add another loop over here, right. So, remember right now what we have done is we have only executed one run, right. Remember that since this is a stochastic algorithm, we need to execute it for multiple times with different seed, right. So, we can also change this Rm value and study the impact of this Rm on the problem, right. So, we leave that to you as an exercise, right. So, if you have any doubts over there, you can post your query in the forum and we will clarify it. So, if you are interested, that you can do is you can have a counter, right. So, we have this f of p which stores the fitness function value, right. So, similarly I can create another variable, let us say something as fees. So, the name of the variable is FEAS, right. So, what this is going to store is if the solution is feasible, it is going to store 1, if the solution is infeasible, it is going to store 0, right. So, over here what we will expect the problem to give the fitness function as well as whether the problem is feasible or not, right. So, same thing I will require in 3 places, right. This is the initial evaluation of the population. Over here and the same thing I will require over here. So, what we are expecting the problem to provide is not only the fitness function value, but also explicitly tell whether the solution is feasible or not, right. So, here we can do comma fees new, or let us say just FES. So, here we will put a if condition if omega is equal to 0, right. So, we are checking whether omega is equal to 0. If it is equal to 0, that is a feasible solution. So, we will return a value of 1. We will just say it is either 1 or it is 0 over here, right. So, we also need to replace this fees, right. So, if the new solution is accepted, whether it is feasible or not, that will also have to be updated, right. So, here we are updating the population, here we are updating the objective function value, here we are updating whether the solution is feasible or not, right. So, this line will also be required over here. So, let me just have a look at it once. So, whether the solution is feasible or not is stored over here, and when we get a new solution, we would also know whether it is feasible or not, and that is updated over here. So, at the end of the algorithm, what we can do is we are identifying the best member. So, here what we can do is, so whether the best solution is feasible or not, this vector FES contains whether a solution is feasible or not. So, we are interested in this particular value, IND because that is the best solution. This will return feasibility, right. So, over here I can also return this feasibility. So, this best solve tells us what is the solution, best fitness tells us what is the fitness function value of this best solve, and this feasibility will be either 1 or 0, right. So, if it is 1, that means this best solve, the solution that we get in this best solve is feasible, else it is infeasible, right. So, we do not have to go back and substitute in this prob again and check, right. So, over here if we come, so this feasibility has been added, right. I can also pass back this FEAS, right. So, this is the entire population in the last generation, this is their corresponding fitness function value, this vector will have either 1 or 0. So, the size of this vector will be the same as the size of the objective function value or the fitness function value, right. So, this will tell us as to how many solutions are feasible in the population, right. So, since we have changed things on this side, right. So, let me just copy this and put it over here. So, here if we see best solve should be the same which we got previously, best fitness should also be the same, right. And now if we see feasibility, we know we had previously explicitly checked this solution by plugging it back into this prob, right. So, right now we do not need to do that, we can just say feasibility, so it is 1. So, this solution which we have is actually a feasible solution, right. From the fitness function it may not be possible to always tell whether it is feasible or not. So, we need to explicitly check whether it is feasible or not, right. So, this is the population, our population size was 5, so these are the 5 members, right. Their corresponding fitness is this, right, and whether they are feasible or not can be obtained from here. So, out of 5 solutions, the last 4 are actually feasible, whereas this is an infeasible solution, right. For constraint optimization problem, you should not only stop with finding out the best fitness function value, but also should ensure that whatever solution is being reported is actually a feasible solution, right. So, that call has to be made whether the solution which we have obtained at the end of the specified number of iterations from any algorithm is actually feasible or not, right. So, that has to be checked. So, here we demonstrated it for teaching learning based optimization, right. So, you can directly plug this file into any of the other 4 meta heuristic techniques which we have studied, right. So, we have already given you the codes of GA, ABC, DE as well as PSO, right. So, you can take this file prob and execute those algorithms to see if you are able to solve constraint optimization problems with those algorithms. With that, we will conclude this session on constraint optimization problem. Thank you.